Welcome to The Explainer. Today, we're taking the abstract, almost magical concept of artificial intelligence and breaking it down into the literal math, memory, metal, and megawatts that make it a physical reality. I am so incredibly excited you're here with us. We hear about AI all the time, right? It's writing essays, it's generating wild art, it's crunching massive data sets. Honestly, it feels like magic. But today, we're going to pop the hood. We're stripping away the illusion to look at the actual anatomy of these systems. And by the end of our time together, you'll see there's no ghost in the machine, just a fascinating, highly orchestrated assembly of physical hardware and some seriously complex mathematical probabilities.
Okay, let's take a super quick look at our roadmap. We're going to cover 1. The AI brain and probability. 2. Vector databases as AI memory. 3. The actual muscle, the AI servers. 4. The home, AI data centers. And finally, number 5, beating the heat with liquid cooling. Let's get right into it.
I want to kick things off with a brilliant little quote from a developer on Reddit that sets the stage perfectly for this entire explainer. LLMs are just giant probability machines pretending to think. You know, as humans, we naturally want to anthropomorphize AI. We kind of want to believe it has a soul or consciousness or that it's sitting there deeply pondering our questions. But as developers are quick to point out, if you just scale up probability, context, and mathematical matching enough, uncertainty itself starts spitting out results that look incredibly intelligent. There's no secret moment where the AI suddenly wakes up. It's really just an enormous probability engine figuring out the absolute best contextual match for the very next token, which is basically just a tiny chunk of a word from its massive vocabulary.
All right, moving into section 1, the AI brain and probability. Let's look at how AI actually thinks, which, spoiler alert, is all about complex math, not biology.
So, the human brain is a total biological marvel. We're talking roughly 86 billion neurons, and every single one connects to thousands of others through synapses. When you see something or hear a sound or have a thought, electrical signals are zipping through those dynamic connections. Now, artificial neural networks definitely take their conceptual inspiration from this setup. They're mathematical models made up of layers of interconnected nodes, what we like to call artificial neurons. But instead of electrical pulses passing through actual biological tissue, it's just data moving through mathematical transformations in a highly structured, very simplified way.
So how does this network actually learn anything? Well, it uses a very structured loop. First up is data preparation, getting millions of examples ready to go. Then comes model training, specifically something called forward propagation. This is where data gets fed into the input layer, moves through these hidden mathematical layers, and spits out a prediction. Next is error calculation. The system essentially looks at its guess and goes, okay, how far off was I from the right answer? And finally, we hit backpropagation. This is where the network literally works backward, adjusting the weights of all those connections based on the error it just made. It uses a mathematical function called gradient descent, which is basically the system's way of finding the lowest possible error rate by gently tweaking and nudging the network into the most accurate configuration over countless iterations. It's wild stuff.
But here's the crucial point. Even though these systems are inspired by us, they learn in a fundamentally different way. We humans are capable of what's called one-shot learning. You show a toddler a picture of a cat one time, and boom, they grasp the abstract concept of a cat for the rest of their life. Their brain dynamically rewires itself. Neural networks, not so much. They usually need thousands or even millions of labeled data points to learn effectively. They rely on fixed layers and rigid mathematical matching. They don't actually understand the abstract concept of a cat. They just understand statistical likelihoods based on a mountain of data.
Okay, so now that we get how it statistically thinks, let's jump into section 2, vector databases as AI memory. How exactly does this thing remember anything?
If you've ever messed around with a chatbot, you've probably noticed it sometimes completely forgets what you were talking about 10 minutes ago. That's because standard models have a pretty limited context window. To actually maintain long-term memory and understand complex overarching tasks, AI can't just rely on short-term processing. It needs a specialized external system built specifically for handling semantic, meaning-based information. This is where we leave traditional databases behind. You know, the kind we've used for decades that store data in rows and columns. When you search a traditional database for shoe, it looks for the exact text string SHOE. But AI needs to understand meaning, and that requires vector databases. In a vector database, data points are indexed as high-dimensional mathematical vectors, or embeddings. So instead of demanding an exact match, the database uses complex similarity measures, like cosine similarity, to find what are called approximate nearest neighbors. Meaning, if you search for sneaker, the vector database inherently knows that it's mathematically and semantically super close to running shoe, or cleat. This setup is literally the long-term memory bank that gives AI its context.
Moving right along from software over to silicone, we hit section 3, the muscle. Let's look at the AI servers actually running these massive probability engines.
You absolutely cannot run modern AI on a standard laptop. A true AI server needs immense parallel processing power. We are talking high-end, 16-plus core CPUs just coordinating the workload. But the undisputed stars of the show? The GPUs. Graphics processing units, like the NVIDIA H100. These chips are absolute beasts at parallel execution, meaning they can solve thousands of math problems simultaneously, which is exactly what a neural network needs. Add in massive amounts of RAM, like 256 gigabytes or way more, and ultra-fast NVMe storage to shove data into the processors without causing a bottleneck. The catch? These specialized GPUs are incredibly power-hungry. They use 2 to 4 times as much energy as your standard CPUs.
Now, all this heavy-duty hardware is split into 2 distinct types of servers. On one side, you have the training servers. These are the absolute heavy lifters. When a company wants to build a massive new language model from scratch, they link thousands of these training servers together just to crunch the data. It requires an astronomical amount of power. On the flip side, we have inference servers. Once a model is fully trained, it gets deployed here. So when you type a prompt into your phone, it goes straight to an inference server. These are hyper-optimized for networking and real-time execution, so they can whip up your answer fast using that already trained model.
Which brings us to section 4, the home. To house all this incredibly powerful, power-hungry muscle, tech giants are building specialized AI data centers on a scale we've never seen before.
$650 billion. Just let that number sink in for a second. That is the estimated amount that major tech companies are projected to spend on building AI data centers globally in the year 2026 alone. The race to build these facilities has kicked off a massive global race for advanced chips, infrastructure, and raw physical power. We are quite literally witnessing one of the largest infrastructure buildouts in modern human history. To really put the sheer scale of this into perspective, look at Amazon's Project Rainier. It's currently being built on 1,200 acres of farmland out in Indiana. When it's finally finished, this single data center complex will draw 2.2 gigawatts of electricity. To give you some context, that is roughly the same power draw as 1 million regular households, just to run servers. And because standard server cooling requires a ton of water, facilities like this also have to pump millions of gallons of water straight out of the ground. This is actually so intense that it's prompted local investigations into residential wells running entirely dry.
So how do we power these hyperscale beasts? It takes massive energy grids. Right now in the US, data centers still lean pretty heavily on fossil fuels. About 40% of the energy comes from natural gas, and coal is actually still supplying around 15%. Renewables are sitting at 24%, and nuclear is at 20%. But here's the thing. Generative AI demands so much constant, uninterruptible, baseload power that tech companies are realizing wind and solar alone probably aren't going to cut it. They are actively exploring and heavily investing in new nuclear options and even off-grid natural gas plants just to keep up with these escalating demands.
And that brings us to the final piece of our anatomy. Section 5, beating the heat with liquid cooling. Because with megawatts of power pumping through rows of servers 24/7, things get really hot, really fast.
Seriously, how do we stop this stuff from just melting down? A single AI server rack can draw 60 kilowatts of power or more. Compare that to a standard data center rack, which only uses about 5 to 10 kilowatts. Standard air cooling fans, which is basically the same technology we've been using since the 1970s, just aren't cutting it anymore. They're deafeningly loud, they consume up to 40% of the facility's power just to spin, and they simply cannot pull heat away from those blistering GPUs fast enough. Engineers have had to get radical.
Enter startups like Ferveret, which was founded by a team of MIT researchers. They had this brilliant realization. The exact same physics used to stop a nuclear reactor from melting down could be adapted to cool AI servers. They created a system called adaptive phase cooling. It's a liquid cooling system that, remarkably, requires absolutely zero water consumption. Zero, which directly solves that massive water waste issue we were talking about earlier.
You've got to hear how this subcooled boiling process works because it's kind of mind-blowing. Instead of just blowing cold air over the racks, the servers are entirely submerged in a specialized, non-toxic liquid that is totally free of PFS, those nasty forever chemicals. As the AI chip heats up, it literally boils the liquid right at the surface of the chip, creating these tiny microbubbles. Those bubbles detach and then rapidly recondense back into the surrounding cooler liquid. Because changing states from a liquid to a gas requires so much raw energy, this process yanks an immense amount of heat away from the chip instantly. It accelerates the heat transfer so well that data centers using this tech can actually generate 35% more AI tokens, meaning 35% more real computational output using the exact same amount of power, and again without wasting a single drop of water.
So let's tie all of this together. The next time you open up your phone and casually ask an AI to, say, write a recipe or summarize a long email, take a second and think about what is actually happening. Your prompt isn't floating up to some magical electronic brain. It's becoming a mathematical probability sequence, matched up inside a vector database memory, activating high-powered GPUs, pulling kilowatts of electricity off the power grid, and literally boiling specialized liquid in a massive data center hundreds of miles away. It's a vast, physical anatomy of math, metal, and megawatts working furiously behind the scenes just to pretend to think. So I'll leave you with this. What part of this massive, sprawling infrastructure do you think is going to be the ultimate bottleneck for the future of AI? Is it going to be the math, the raw power, or simply the heat? Definitely something to think about. Thanks for joining me on this explainer, and keep learning.